Here's a simple machine to illustrate how the fractals of the Habermas schemata operate. Although the example has only a handful of fractal atoms, the principles demonstrated here should scale to very large machines with perhaps thousands or millions of elements. The beauty of the Habermas schemata is that everything known about the world, from the thing is red to that's my grandmother, is held in a network of common elements called fractals. The 3-bit assimilator is shown in the Fractal Workbench application. It learns bit patterns on its lower world ports to form a network which recognizes them. Each fractal element holds a bit of cognitive state comprising a have signal going up in green and a want signal going down in red. The green have going up indicates how much we have evidence that the state is true. The red want going down indicates how much we want to have it become true. Black represents both red and green. Now we describe in detail how each of these 3 patterns are learned as they are experienced. We start with the model empty, no notion of the world there. Then the first pattern arrives with both A and B on. The green signal flows up from the bottom through the model splitter, since there's no model there, to the record heads as unknowns. To record the coincidence A and B, the right head adds an element connecting them. Once added, there are no more unknowns. Next, the sample has B and C on. This coincidence is unknown to the model, so the record head generates another element to the model to record it. The next sample has C and A on, and a third element is added to the model. Now, if just these 3 patterns reoccur, they are recognized without adding new elements. This is how the 3-bit assimilator learns to recognize patterns. At its core, it's so simple. In future lectures, we will show how these core ideas can be extended to make huge machines. This involves our plan for how experiences can be sorted into contexts, how large distributed associative memories can be formed, integrating data from multiple domains, how state transitions can be learned, how they can be made conditional, and how the conditions that enable them learned, and much more. With all this, the machine builds a distributed forward model used for prediction and understanding. Hierarchically and with bidirectional elements, I'm Alan King, the backroom algorithmist, and this is my plan.